We'd like to prove the central angle theorem that says if you have 2 points on a circle, Q and R, then the central angle, so the angle that these 2 points make at the center, beta in this picture, that angle is twice this angle alpha, which is an inscribed angle, QPR. Now, in class, you guys proved this using this type of drawing where the center is inside the inscribed angle. Now, unfortunately, the argument that you made isn't going to hold for all cases. So if we move P around here so that the center no longer is inside, you'll find that the arguments that you made are no longer valid. The triangles you referred to, they're not there anymore. There's actually, unfortunately, it's even more complicated because there's a third case, which is the case where the line for the inscribed angle goes straight through the center. Unfortunately, to completely prove this theorem, we're going to have to prove this separately for all three cases, both where the center is inside the inscribed angle like this, where the center is on one of the lines of the inscribed angle, and where the center is outside the inscribed angle. There's, as far as I know, no shortcut. You've got to do all three. So we'll start with the case where the center is inside the inscribed angle. Now, let's add a couple of lines here. We've already added the line from P to C that's a help line. We'll divide this angle alpha up into two. This one, which I can call X, and this one here, which we can call Y. Now, if you note that this triangle, PCQ, it's isosceles because one of the sides, PC, is the radius of the circle, and so is the side CQ. So this angle is also X. And in the same way, this triangle, PCR, is isosceles, so this angle is also Y. Then we can use that, well, let's label these two. We can call this one, say, S, and this one T. Then we can note that the sum of the angles in this triangle, PCQ, and in PCR, together they give us 360 degrees. It's two triangles, 180 degrees each. So we can write that like this. It's 2x plus s, that's the angles in triangle PCQ, plus 2y plus t, that's the angles in PCR. The sum there is 360 degrees. That's two triangles worth of angles. And then if we look here at the center, around point C, we can easily see that S plus T plus beta is equal to 360 degrees. So we can equate these two. We've got 2x plus 2y, I'm changing the order a little bit here, plus s plus t is equal to beta plus s plus t. And the s and t's cancel. So we get beta is equal to 2x plus 2y. But of course, x plus y is equal to alpha. So beta is equal to 2 alpha, which is what we wanted to prove. Now let's have a look at the second case. This is where the center of the circle actually lies on one of the lines of the inscribed angle, alpha. So here we can see that PCQ again is an isosceles triangle. That tells us that this angle here is equal to our angle alpha. We can also see that the sum of these angles here is 180. Let's label this one. We can just call it x. X isn't a very conventional name for an angle, but it'll do. And we can see here that 2 alpha plus x is equal to 180 degrees because they're the interior angles of a triangle, PCQ. Then we also see that beta plus x is equal to 180 degrees, and that's because they're obviously supplementary. So from these two equations, we immediately see that 2 alpha is equal to beta, which is what we wanted to show. And finally, the last case, where the center of the circle is outside the inscribed angle completely. Now this, I think, is kind of the trickiest one. We'll label some more angles here. You can see we've still got our help line from P to C. So I'm going to label this larger angle here. I'm going to call that X now. And this smaller angle, this one, let's use a different color. I'm going to call that one Y. And you can see here that PCR is isosceles, the same reason we've seen before. So I can label this one also Y. And we also have that PCQ is isosceles, so we've got another angle here, which I can label X. Now, if we look here at C, well, let's label one more angle. We'll call this one R. Now we can see that R plus 2x is equal to 180 degrees. And we also have here that if we look at this triangle, PCR, we have that 2y plus r plus beta is equal to 180 degrees. Now we can equate these two, so we get r plus 2x is equal to 2y plus r plus beta. Now we can cancel those r's since we've got one on both sides. Let's move the 2y over to the other side by subtraction. So we get 2, and I'm going to group the x and y. 2 times x minus y is equal to beta. But if we look here, x minus y is just alpha. So we end up with 2 alpha equal to beta, which is what we wanted to prove. We've now proved all three possible cases, which means that this theorem holds for all positions of P. Well, that's not strictly true. If we put P here on the arc QR, then we run into problems because it's not entirely well defined. That's not going to work. But as long as P stays outside of the arc QR, we're fine, and the theorem is proven.